Let's see if I can become a better coder through this video.
Hi there. There are what I would consider to be 7 deadly sins when it comes to programming. Things that will grind your code quality into dust if you don't heed their lessons. Now, I hope you've never had to hear someone tell you that you write bad code, but if you have, there's really nothing to be embarrassed about.
True.
We will write flawed code as we learn, and the good news is, it's fairly straightforward to make improvements if you're willing. In essence, that's why I've created this video, to guide you to becoming a better coder.
Tip number 1, which I don't think is in this video. Don't say coder. You will buy osmosis if you listen to the people who say program and programmer. You will get on average a lot better advice, I think, than those who say coder. But let's continue.
So let's look at the mistakes you might be making and see if we can fix them. The first thing I see people doing is not using programming standards. They give us rules to follow.
When you're new, I think this could be pretty good advice, but you've got to remember that most programmers aren't that good. So you can imagine most standards aren't that good. And therefore, you at some point have to develop your own way to judge, was this useful to me in achieving a real world end result? How did this help me ship? How did this help me deliver value? Is the better way to say it. How did this help me deliver value to an end customer? And if it's not helping with that, then maybe it isn't actually that good.
Like white spacing, file structure, and other philosophies that we apply to make our code consistent and therefore easily readable. It's also especially important when working with other people because it allows everyone to rely on shared expectations. If you don't keep standards, it's kind of like switching fonts all the time. We can read it, sure, but the subtle differences throw us off and slow us down a bit.
This, I think, is a good point, although I think personally that if you're new to programming and you're learning, you should be spending most of your time working alone, because that's how you're going to be able to put in the time to get good. Being on a team when you're early probably does happen to a lot of people, and isn't optimal. So yeah, this switching between fonts thing analogy he's using, it's absolutely correct. I agree with this. Although, of course, most of the standards aren't good. So, but that's probably more general patterns and stuff.
As for choosing a standard, if you aren't given one by your team, then there's plenty to choose from in the wild. The second thing, programming design principles, are probably some of my favorite ways to improve. You can think of principles like a general guide into becoming a better programmer. They're the raw philosophies of code. Now, there's a lot of principles out there, too many to cover in this video, but I will quickly show 5 very important ones which go under the acronym of SOLID.
Already, we're off to a terrible start with this video. I'm expecting strict misinformation from this point onwards. Do not use solid principles. And this is again why you should spend so much time programming on your own, because if you program on your own without the social, like, think about this, the best programmers are often the least social ones. And why is that? It's because by not talking to anybody else, they don't succumb to social diseases of bad ideas that are floating around. This being one of them, a big major offender.
The S in SOLID stands for single responsibility, and it teaches us that we should aim to break our code down into modules of one responsibility each. So, if we have a big class that is performing unrelated jobs, for example, we should split that up into separate classes to avoid violating the principle. It's more code, yeah, but we can now easily identify what the class is trying to do, test it more cleanly, and we can reuse parts of it.
already, I mean, you shouldn't use classes in my opinion to begin with. So, but if we set that mistake aside, in theory, there's nothing wrong with putting the code that does a certain job apart from other code. But if you follow this principle, you easily end up with the typical like OOP code base where it's a million files and you can never find anything because it's all been shattered up based on this principle into lots of tiny pieces. If something is doing a lot of work, that's good. Actually, you have context, right? If you pull out a piece of code somewhere else, now you can't, when you read it, you don't know what context it's being used in. And that lack of information actually causes you to have a poor understanding, make poorer decisions. You actually want things maximally integrated and only split things off into their own separate modules or whatever when you have to, when that is either a very good split on the real problem that you have. So say in compilers you might have like, oh, the tokenizer is it's kind of its own job, so we'll separate that out to the side. Although something like LLVM is a thing used in compilers and is massively slow because they separate things out way too much. And something like negates TB or quick C compiler can be super, super fast because it actually merges together several stages of the compiler to do more work at the same time, because it turns out that's faster. So anyway, probably if you're a noob, you shouldn't pay that much attention. Just there are many, many, many cases, in fact most cases, I would argue, where this does not apply. And most importantly, following this does not in any way help you get any closer to the solution of your problem, and that is where you need to be single-mindedly aiming at the goal, at your destination, because otherwise you'll just walk in circles and you won't make any progress. You'll feel like you're doing things, but actually you're doing nothing. Moving things around in which file it's in or which class or whatever is not being productive. That's not working. That's moving papers around on your desk. Okay, let's continue with the video, although I expect to be disappointed.
Fit elsewhere, without having to worry about irrelevant methods at the same time. This actually becomes more important as we progress. The open-close principle suggests that we design our modules to be able to add new functionality in the future without having to actually make changes to them.
That is terrible advice, because you have access to the module. Okay, there's this big confusion in much of this advice where somehow advice for good library design potentially got mixed in with just making a program. Many people are confused. They adopt behaviors for making a library when they're actually making a program. Okay? You have access to the source code of the module. So just edit the module to add the functionality. You don't need to make your module or piece of code, system or whatever. You don't need to make it more complicated in order so that you don't need to edit it in order to add new functionality. Because you could just edit it, and I guarantee that it'll be simpler and it'll help you get stuff done faster. Just don't. This is a waste of time. This is for, I don't know who came up with this.
Instead, we should extend a module to add to it, be that wrapping it or something else, but we should never modify it directly.
Why? Why? Always with these rules, it never goes explained. It's just, oh, never do this thing that I made up that you should never do. Why? I don't know why. The programming gods said so.
Once a module is in use, it's locked, and this now reduces the chances of any new additions breaking your code.
That's not true either, though, because if you subclass, the subclass is like doing stuff with the functions, and so if it's any interesting type of behavior, it's going to lead to breakage. Again, just edit the module, okay? Just edit the module, fix mistakes if you make them. You'll be way faster.
Luckily, the Luminous Liskov leaves us a lesson that loosely limits how we leverage our legacy code. Okay, that's enough of that. Liskov wants to tell us that we should only extend modules when we're absolutely sure that it's still the same type at heart. For example, we can probably extend a hexagon into a 6-pointed star, because that still makes sense as a 6-sided shape. But we can't really do the same if we wanted a 5 or 7-pointed star.
Yes, you can! Well, no, just modify the... Just modify the code. Don't extend and stuff. Yeah, anyone who uses... Just, it's... I'm lost for words. This is not good.
Because that would no longer be compatible with what a hexagon represents. It just wouldn't fit cleanly anymore into parts of your code that expect hexagons. And
yes,
so it
they have to change when I add new
functionality. If that's the case, it should extend something that fits its design or become its own type instead. Almost at the end now, and we have I for interface segregation. It says that our modules shouldn't need to know about functionality that they don't use. We need to split our modules into smaller abstractions, like interfaces, which we can then compose to form an exact set of functionality that the module requires. This becomes especially useful when testing, as it allows us to mock out only the functionality that each module needs.
Why can you not just modify the code? I mean, he said mocking here, which...
as it allows us to mock...
I mean, I've built very complicated things, and I never, ever have used mocking and found it useful. And if you want to mock effectively, why is it not just... Like, you can just build that into the code. That could be... That's like an if-def. If-def this, you know, if we're compiling with mock, blah, blah, blah. Like, for example, for... Like, if you're making a game or something and it's a networked game, one... thing you can do is you build a system into the game for recording the network traffic so that you can replay it later on. You can do this for input as well, where you build a system into your input system. Where you build this thing so, I can hit record, play the game, do a bunch of things, and now I press stop. And now I can debug my game and I can test my game by rerunning it with the same inputs that I recorded. These are things you can build into the program, and you can use them to trigger parts of the code in order to test them. You don't need to do this weird special interface thingy.
Out only the functionality that each module needs. Which brings me to Big D, which stands for dependency inversion. This one is pretty simple to explain because it says that instead of talking to other parts of your code directly, we should always communicate abstractly, typically via the interfaces we define. Dependency inversion breaks down any direct relationships between our code and
Why? If I don't have direct relationships between the code, then I have less context, so I can make... My understanding of the program goes down because you've obfuscated it. Just because you've made it harder to understand the entire program doesn't mean you understand it more. It's the complexity is still there. You've just hidden the complexity so that it's harder to look at. And when it's harder to look at, it's harder to debug because you don't know. You're going to see a call to one of these interfaces and you don't know where it's going. Versus if you call other modules directly, you know when reading the code where that's going. There are no questions.
Isolates our modules completely from one another, meaning we can swap out parts as we need to. Because they communicate with interfaces now, they don't need to know what implementation they are getting, only that they take certain.
But if I don't know which implementation I'm getting, how am I supposed to debug the program? And also, again, this is going back to this thing I was talking about, where somehow people think it's your job as a programmer is to write, any application is this network of libraries that you made. No, it's a machine. It's a one machine that does one job, and so you don't artificially split it up into teeny libraries and then I can swap in and out components as I need. Why? Don't do that until you actually have a use for doing this swapping in, swapping out. He doesn't mention that here. He just says, hey, if we do it this way, then we can just swap things in and out. Why do we want to swap things in and out? Is that not more complicated and difficult to understand? Which version of the program are you running? Is it with A swapped in or version B swapped in? Is it this config? Did you turn on the blah, blah, blah? No, none of that. Just you want the thing that's simple. And the thing that's simple is not having this added complication of I'm going to obfuscate what is happening because that's cooler somehow. It's really bad.
Inputs and return a valid output. The cool thing about Solid is that when we combine all these principles together, it ends up decoupling our code, giving us modules that are...
Except if it's like Mike Angton says, you can't like pretend yourself away from the problem. You have an actual problem you're trying to solve, and if you like decouple parts of this problem, then you just have like, now my problem is more complicated because I have to deal with the fundamental problem and the problems I invented by splitting my thing up in this way where they have to do this complicated communication across various stateful systems. It's crazy. No, solve the actual problem in the simplest way. That's how you program well. And okay, if then on top of that, you notice that, oh, some things are quite unrelated to others, so I'm going to separate those in my conception, then that's perfectly fine. That's good. That's organized. That's having noticed something about the reality of the problem, not force your own decoupling onto the code.
Independent of each other and making our code more maintainable, scalable, reusable, and testable. Programming design patterns, not to be confused with principles from the last chapter, are also something I see underused a lot, when they really should have more of a place in your mind. Patterns give us some real solutions to our code problems, but they aren't fixed implementations, so they're still kind of open to interpretation. We use them to architect our software systems, matching the right shapes to fit the needs our software has. First up, we have creational patterns, which are there to help us make and control new object instances, such as the factory method pattern, which turns a bunch of requirements into different modules that follow the same interface, but aren't necessarily the same type.
This is a very bad pattern.
Then there's structural patterns, which are concerned with how we organize and manipulate our objects, such as the adapter pattern.
You shouldn't be thinking about it.
Wrap a module and adapt its interface to one that another module needs.
Okay, this is ridiculous. This is having an adapter does not need its own name or its own introduction.
Finally, there's behavioral patterns, which focus on how code functions and how it handles communication with other parts of the code, such as using the observer pattern to publish and subscribe to a stream of messages in an event-based sort of architecture.
Look, this is why I said as well that in the beginning that as a noob you just should spend lots of time programming on your own shipping real products, be that games or something else, because as you build things, these patterns, teaching somebody explicitly these patterns is a poor substitute for the intuition you build of how it goes. And I mean, it's a little bit like the thing he showed there in the beginning where you're trying to match in the pieces. But what you want is not like, oh, I heard about this pattern, let me explicitly remember the pattern and like try to apply it. Is what you want to build is the intuition for, oh, I'm trying to solve this type of sub-problem. How can I go about doing that? What is the solution to my problem? Right? And maybe these patterns are useful in that way. When I learned don't think ever learned any of these patterns or whatever. And most of them are so simple. It's like you gave a name to something that doesn't deserve a name because you cannot describe it in more words than the name itself. It's like that observer pattern. Okay, I can say observer pattern, or being able to subscribe to events. Okay, that did not deserve a word of its own. That's just, well, I have events and you can subscribe to them. Not that hard.
Now, there's a bunch of different design patterns under each category. Some of them you might have used before. A lot of these patterns are used by frameworks and by professionals in huge corporations. And that kind of ties in with another pretty unique
That's why
benefit.
the stuff they make
The
isn't that
benefit
good.
of creating a universal vocabulary of programming. Have you ever written some code that seemed great at the time, but later you had trouble understanding it? Well, it often comes down to the way you name things. Take a look at this snippet. It's quite short, but it's hard to interpret what's going on without some thoughtful analysis. Let's fix this in steps. First up, we should avoid unnecessary encodings, such as type information.
This is wrong because many times the type of the thing may be important for the behavior. And so if I put, in this case, if I put list in the name, then that's communicating something. If you remove it, then I've lost information while reading this code on what the types are, that's not good in my opinion.
Which make it harder to read code in a natural way.
And don't take that as you should always write the type, because it's nuanced. And again, this is why you need so much solo practice, because you get to see how it goes and when you want this and when you don't want it.
Next, we have many abbreviations and acronyms that don't really explain well enough what they are. We should expand them to their full names to avoid any miscommunication.
This I actually fully agree with. Don't make something worse because you were lazy. You know, be a serious grown-up person. Spell out words. You can do it. I believe in you.
Looking better, but it's not really clear what some of these variables hold. They're quite vague and ambiguous. We should aim to use names that more accurately represent the nuances of the code we're working with. We also want to replace magic values, such as the organ index or trigger word string, with named constants.
In theory, yes, this is good, except now I don't know what the value of the constant is. You know, if I am looking at it and I'm trying to... The programming language obviously doesn't care if you use the constant or if you put a literal in the code. But me as a human, when I'm reading the code, if I see the literal, I actually know what value that is. Versus if you put a constant, well, I have no idea. Now I don't know what that is. You know, I think the actual argument for constants would be to not make a mistake, like a typo in the literal somewhere. But in terms of readability, again, you're removing information. Now I have to go see, oh, what is brain? Now I have to look up my literals in some separate table to go, oh, what was the value of this? I guess maybe the reason people suggest this is because the code they're used to working with is so short and does nothing that this doesn't become a problem. But when you have like a 20,000 line function, which is not that uncommon for big projects. I mean, most of my stuff is not that big, but say, you know, you have a 6,000 line function, that could easily happen. Or just, you know, you have something big and you put a constant in there. I don't know what the constant has for value, especially if that constant matters in some way. I guess for most people, most people's code they write, the value doesn't matter that much. But then when you're in the debugger, you know, if you're in the debugger and you look at some variable, it will show you the value in the same way as the literal, it won't show you the name of the constant. And so if you use a literal, you could say, that's the same, it just got assigned from over here because I know what it got assigned to. So I think it helps you in that way to keep the literals.
By doing so, we clarify their significance, and we help to keep things in sync if they're used elsewhere. Okay.
So the keeping them in sync, that's the real argument here.
We can now read this code and understand what it's doing without having to think too hard about it. However, we can still improve it further. If you have any compassion for your future self, or other unfortunate developers who might have to read your code, be descriptive with your names.
This is good.
Ideally,
This is good. We love long names. Love them.
we want to find a balance between being clear enough to quickly understand what the code does, without being so verbose that it becomes an information overload. Remember that no matter how good you think your code is, if it's not easy to read, I would argue that it's not actually good code at all. Many people don't test their code, and that's understandable, I think. Writing tests can be very difficult when code is not properly architected. At the high level, we have end-to-end testing, which lets you test the system as if
This
you were
stuff
being
is really
user.
good. It's what you should be using.
Because literally any spaghetti code could be end-to-end tested, assuming you can simulate the inputs, as it never actually touches the code itself, only what it delivers to us. They can be tricky to set up, though, due to the need to always have a fully functional application running, but they are surprisingly valuable.
If you don't have a fully functioning application running, I would question what you're doing. Because if you don't have a fully functioning application, or at least something you can run, then are you solving a real problem, or are you just like pushing the papers around for fun? Because if you're doing that, then I don't see why you need to test it, because it doesn't do anything yet.
At the lower level, we have unit tests to verify the operation of our modules in isolation, and integration tests to examine the interaction between those modules.
You know, there's this saying that the carpenter who makes, say, a table, he actually, like in his mind, has the shape of his table, or has the shape of the table inside his mind, because he's the mold that created it. And I think there's no way to really test a unit test code without writing the functionality again, if you want to be really rigorous. Because otherwise you're just testing one-off example cases, and you might as well just end-to-end test your full application. And also, if you can't get to the functionality that you're trying to use from some end-to-end testing. I mean, end-to-end testing doesn't have to be the application. It could be the subsystem. Like, I have this collision system, and so I have this large data set of collision stuff that I'm testing through this. That's obviously useful. But you should be testing at the level where you are delivering a solution to a real-world problem that exists. Testing small pieces of your thing, I guess people do that because they don't have debuggers, and so they can't actually go inside that program and like figure out what's happening at runtime, and so they feel like they need to rigorously test each small part. I guess as well, if you work in something like Python, you have to have unit tests, because if you aren't running all the code, then you don't know if the code will explode because of a typo. It's just so, your ability to ship reliable software is just so low that you have to run a bunch of tests to then have coverage, which is actually type safety, because you just have executed the code, and that's what you need to do to type check it, which is just all kinds of crazy.
These provide validation that our code is doing what we expect it to, rather than focusing more on behavior, like end-to-end tests. If the thought of writing tests seems overwhelming right now, try applying the solid principles you learned earlier. You might be surprised at how much easier it becomes when your code is modular and decoupled.
Yeah, if you spend all your time making libraries that you plug together and take way longer, then yes, it'll be easier to test those components. But that's a waste of your time. Just write the app or whatever and try it. Use it. Be a user of your own software, and you will notice when it doesn't work. And when it doesn't work, you fix it. It's that easy.
Number 6 is time and how you manage it. Time estimation is a process I still fail in sometimes. A common rule of thumb is to double or even triple your initial time estimate for a task. It feels excessive, but it's impossible to predict the unknown problems we will encounter along the way, so we need to account for those. For example, this video took 3 times as long to make as I had predicted. I really should take my own advice sometimes.
Don't have much
Remember
to
that
comment here.
creation goes hand in hand with problems, so in the end, it's better to overestimate and deliver ahead of schedule than it is to miss a deadline.
There's a Mike Actonism here, which is very good. He says that, okay, so you have this deadline. You know, for some industries, deadlines actually matter. You can't just blow past them and it's fine. Most of the time, deadlines actually matter. And what you need to do then is you say, okay, this is the time I have. Here's the solution I imagine to build in this time. When 2 days before the deadline, my system isn't working and I have to scrap together some emergency last-minute solution to make it work, to ship the game, to make the demo, etc. What you do is that you say, what will I do the last day or two to rush for this deadline? Make that solution first, okay? Because now, like, you're doing the same amount of work either way. It's just now people aren't stressed and worried that you're going to ruin everything by not having delivered on time. And actually, most of the time, you'll realize that this crappy thing that you put together last minute, but you actually did it first. You do that first, and you realize, oh, actually, this is good enough. It solves the problem. I don't need the more complicated thing I was planning to make. And then you actually just finish early. And if it's not good enough, if you think you can ship something better, then you can take the time to try ship that within the allotted time frame after you've done the appropriate, time trade-off of, is this worth it, or should I work on something else instead?
Alright, this one is a bit cheeky, as it's still kind of related to time, but I needed 7, not 6 points to make the Deadly Sins reference, so
Understandable.
here we are. All I wanted to say here is that you should try not to rush. Things can feel great when we're blazing through a project, and there's definitely a place for that in prototypes. But remember that if this is going to be a long-term project, take your time and think things through from day one. We'll never get all our decisions right first time, but we can at least give ourselves a better foundation to work from, and hopefully avoid some of that nasty code debt later.
I don't believe in code debt in this way. Future you always knows more. Almost always knows more. And so you should err on the side of, well, I'm going to be a smarter programmer when I come back to this, so I won't try to prepare for the future. Sometimes you can successfully do that, or if it's, I actually know that we will be replacing this code with something else at a later date. That's actually, you do want that. You want, when you write the code, how long is this going to exist for? Many times it's, I'm writing this, it's only going to be used for the next, 8 months, and then I'm going to rewrite it with something else when I know more about this problem space. That's a very good attitude to have, because then you can move faster. And this technical debt thing actually never shows up. That only shows up at like web shops or people who write. People who write according to the solid principles mentioned earlier in the video, they get this technical debt thing. The people who just actually try to solve problems don't end up with technical debt.
Anyway, you're likely to finish in less time regardless if you're not constantly battling decisions you can't easily fix because of poor architecture. We want projects that get easier with time, not harder. And that's it. Wow, you leveled up. Go forth and be the programmer you were always meant to be. I'd like to end with a quote from Martin Fowler. Any fool can write code that a computer can understand. Good programmers write code that humans can understand.
That's a good quote, but don't abuse it. And don't pay attention to it as a noob. You need to know how it goes first from lots of programming yourself. All right, well, that's it. If you like the content of this video and want to see what I actually do for my main project, well, you can head over to samhsmith.com/Serenum, where I'm making an operating system from scratch on my own machine hardware thing that I sell. And we're rebuilding all of software to be actually good. It's all completely from scratch. I've done the programming language from scratch, compiler, you name it. I'm working on Wi-Fi right now. That's going to be very exciting. The previous update had a window manager. I built this window manager using the machine. So I bootstrapped myself up from the old environment to this cool thing. Anyway, with that, have a good evening, everybody. And I'll see you in the next video.